Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon, everyone. It's my pleasure to introduce our visitor today and tomorrow, Klaus Ehrlich, who is at the University of Munich, and he did a PhD in 2003 from the same university, and he's been working on mathematical logics, proof logics, and now the lambda calculus that we'll hear about. Welcome.
Okay, so thank you very much. My talk today will be about normalization by evaluation, which is a technique to get the normal form of symbolic expression. And we implemented that into Isabelle, and I'll talk a bit about the implementation and the way we did it here, and also about the verification we used. So why do we want symbolic evaluation in a theorem prover? Or first, why do we want evaluation at all in a theorem prover? And well, the main reason is that a lot of theorems that are formalized involve heavy computation, like the four-color theorem, where at the end you boil it down to a finite number of cases and then try them all more or less automatically. And also recently the Kepler conjecture involves a lot of computation with these numerical things, and you want to make sure that this is correct. And as I said, it's a lot of computation, so you better want it fast instead of slowly doing symbolic transformations, but you still want to base it on a theory. And actually, well, that's the general idea. Computation is something what a computer is good at anyway, so we can, from some formal theory, generate some code, run it, look at the result, and since we generated the code from the theory, we have a fine relation between the code and the theory. But what we also need is, symbolic evaluation. That is, compute with terms that have free variables, uninterpreted function symbols or uninterpreted constants in them, or we want to argue about functions which then are under some functional abstraction. And that's useful, well, if you start formalizing something in your theorem prover, then you want to get some feeling whether you've formalized things right, explore the definitions, what does this program do on a general 3-element list, or things like that. Or within a formal proof, you're in a proof state, you have a lot of symbolic expressions accumulated, and you want to simplify them and compute with them. So explore what a program does on general inputs or simplification within a complicated proof state. So what do we want to do? We want to compute normal forms of symbolic expressions with respect to, well, beta reduction. That is, you have a function applied to some argument, then these arguments are put into the definition of the function, which we write that way in the lambda calculus. And with respect to some equations, which could be just the defining equations of some function, which usually involves pattern matching. Here the definition of the addition. But also arbitrary term rewriting rules, which is useful in theorem proving if you prove some equations hold between your function. And once you've proved them, you want to also get normalization with respect to them. Do we get forward? Yeah. And as I mentioned, that's easy if we have only ground terms, so terms without free variables. But we still want to do this in the presence of variables. That could be either just some completely free uninterpreted variable as the b in this example, or some variables which further out are bound by some abstraction, saying that's a function which maps a to this expression, which happens to have a free variable in it. Okay, so I said the general approach is we compile the term into some ML code, then evaluate the ML code, just the normal evaluation process of our language, and then look at the result and get a term back from that. And I said that works fine as long as it's a closed term of ground type. Then we can just compile it, more or less literally translate our symbolic term into ML. run it there very fast because it's really at machine level, and look at the result. And in most cases, that's what you really want to do, and that's useful and that works fast. But as I said, we're also interested for exploration of definitions to do it at least reasonably fast, but with uninterpreted variables. Yes?
So you generate ML code from Isabelle?
Yes. And for closed term that existed for quite a while. And now what I'm talking about is how you do it in the presence of free variables.
Okay,
so that goes through the Colby value, yeah. Well, if it's in Isabelle you only can introduce a function once you've proved that it's a well-defined total function. So all the objects, all the code you're generating normally, if you're only doing it with respect to the definition of a function, then you already proved that it's terminating. So yeah.
So you don't need to do
any fancy thing. No, they don't need. If you do it as we do with respect to arbitrary rewrite rules, then of course you can't expect termination. For example, you could prove addition being commutative and then flipping back and forth all the time. So we don't guarantee termination, but still we want to compute in the case where it does terminate with symbolic expressions, but not by just doing substitutions and term rewriting, but compiling it down at least reasonably far to the machine. Okay, and so the main part of the talk is explaining how we do this. So as I said, the key point is we have to, in some way, handle free variables. So we need, as I said, we go to ML, we need a type in ML where we do our things in, and it must be able to speak about free variables, so syntactical objects of our language. On the other hand, we want to compute evaluate functions or compute with functions, so it should contain the function space as well. So we need a data type containing some syntactical entities and functions. Well, let's do a very naive attempt. In ML, we can write a data type like this. A universal type is either a string or a variable which is indexed by a string with the name of the variable, or it's a function which then is an object of universal type to universal type. Such types exist in ML, and that's the first approach how you could try and do it. Unfortunately, we're not yet finished. Because I said we want this to be a model of the lambda calculus or of some functional programming language. If you have a variable that stands for a function, in some way I have to say, oh, I have to apply this variable to some arguments. So we have to give an idea what it's supposed to mean a variable applied to some value of our general data type. So that's essentially the main problem what normalization by evaluation is about. What is this supposed to mean a variable applied to a value? Well, the good thing is that if you have a variable and apply it to lots of arguments, we know in advance that we'll never be able to simplify any further because the variable is uninterpreted and there's no simplification rule we can apply to that variable. So what we do is we just collect all the arguments ever applied to it. So we slightly modify our data type saying it's a variable, which is a string, and then a list of objects applied to it, which we then normalize individually, but don't look into them. So we just collect the arguments, and then we can define application. Well, if it's a variable, then we have this list of values already collected, and we just add to that list. And if it's a function, well, then we can use the function application of our underlying language. And the other thing, as I said, well, I kind of justified this extension by collecting arguments to a variable by saying it will never cause a radix or the need to simplify any further. And this idea can be made a bit more formal by saying, well, from our universal data type, we can get a term representation back of the object denoted by it, and it will always be normal. There won't be any further simplifications possible. And it's very easy to do. We have two kinds of data. It's either a variable with some arguments applied to it, while getting a syntactical representation of a syntactical object is easy. You just take the variable itself. Maybe I use the laser pointer. So getting a so this is what this function term is supposed to do. Yeah? Question?
So in terms of background of this approach, is this what you would call high order abstract syntax based? Is it
Yeah, you could see this universal data type as higher order abstract syntax. And it's also related to what you do with partial evaluation of a program. You just build the program, run it as long as you got, as long as you can do anything. The way I like to see it, say, well, it's a type of, the way I like to see it, is it's a type of normal forms of our object. Because if it's a variable with arguments applied, then, well, that's at least in head normal form. And it represents a term, well, starting with the very same variable. And then you take the term representation of the arguments collected and just use the term application, the some syntactical form application, and build the corresponding term, xt vector. And if it's a function, well, functions are in a sense also in head normal form. They're values at ML level or whatever. You say you take a fresh variable, which you can write a lot of papers about, but in practice you can ever say, well, just have a global counter, which gives you a new symbol. Take a new variable, apply this function to the variable, and then abstract it symbolically. And that gives you a term starting with lambda x, and then by some form of induction, something normal. So, and if you're only interested in the pure untyped lambda calculus, that's all you do, and it works fine. But as I said, we want this to mainly symbolically evaluate programs or simplify terms in some theorem prover. So we need some data constructors at the very least. Well, just do the same thing again. We need data constructors in our type, so we just add them. And again, the question, what is it supposed to mean if you have a data constructor applied to some argument? Well, again, if it's a data constructor, success of something will never cause a radix. That's the idea of constructors, that they are free in the sense that they never cause any means to simplify things. So we just do the same thing again. We collect the arguments and extend the application the obvious way. If you apply a constructor to more arguments, then you just collect further. And if you work in a theorem prover or something, if you have a slight technical thing, a function might have hierarchy. So you not necessarily do all the currying, but say you want at least 2 arguments before you start before you can check whether there are any simplification. The standard example is this minimum function, which has a runtime linear in the smaller argument, where essentially you check either the first or the second argument, whether it's 0, and then you stop, and otherwise descend in both arguments. So before we can check before we can evaluate that function, we need 2 arguments collected. So, well, we allow n-array functions. So in our type, we add constant saying what is the arity, and it's a function. Well, we want it universally. You don't want to have here n constructors for all the possible arities, which would be a way to code it. But for simplicity, we say, well, just take a list of universal objects. And again, if we have a function of higher arity and we only get 1 argument, then, well, we collect until we have enough.
So you compile into ML. So the standard ML compiler, as far as I know, doesn't treats multiple arguments as tuples, sort of boxes the arguments, and
yes,
the advantage of having multi-arity functions it doesn't really.
So at the ML level, yeah, we compile it into ML function that take a list. At the theory level, we want to deal function with functions hierarchy because we want to deal with that kind of definitions. And there you obviously need...
Why can't we deal with this definition that the curry here?
Well, you can, but then... well, you can curry it, but at some point you have to say, well, I do a pattern matching against both arguments. Especially at this last line, you really have to have both arguments present before you can decide which rule to apply.
And there's no counterpart of curried matching.
Well, there's no counterpart of curried.
You could have introduced a case statement, right?
I could.
Your data type, instead of having lists of arguments.
Arguments, yeah. Or I could say, since I compile before running anything, I could have a data type which has as many constructors for the arity as I need, and then have, yeah.
So now you're mixing function closures with pattern matching, right? So you could have separated them out.
It is separated, so it's the closures.
We just have curried functions.
Okay, and then
then a case statement on tuples of things.
Yeah.
Above definition gets de Schubert too, right?
Yeah. And it's not that far from, well, I think on the next slide I have this compilation of functions anyway. But it's not that far from what we do. We say it's a function, and I only want to do the pattern matching once I've collected n arguments. And then here you have an ML function, which expects a list of length 2 and does some pattern matching on it. So in a sense, it's not that much different from... Oh, you have this kind of handling of the closures and the currying separated from the actual function doing the pattern matching. And I think, yeah, on the next slide. That's a good question, actually, because it gets me to the next slide. There's one detail we have to solve. How do we translate functions, function from the symbolic term level, as I just shown, to ML level at our universal data type? So let's take that example, because it adds up, shows a nice property afterwards. So take we want the append function, where you actually don't need the currying because you're completely parametric in the second argument. Anyway, so if you go back to it, in our universal data type, we say it is a function, and here we need an ML function getting a list of universal objects of the universal data type to an element of the universal data type. So we have to compile it down. So we need a function that takes a list of length 2 with the 2 arguments and returns something of our universal data type. And, well, it's supposed to do the pattern matching and hopefully efficiently. Well, we can, fortunately, we just added the constructors of our data types into this universal type, so we can just do pattern match against these constructors. And here I'm slightly lying on that slide. That's with our first implementation. Actually, what we do is we are not matching strings, but matching integers, which then gives you another speed up. But anyway, you have these constructors, you have these constants, you can do pattern matching against them. And then you just write, well, here, variable is easy, and if you have a constructor, then you can write it out. Looks nice. The bad thing is that's not an exhaustive case distinction. Here, for the symbolic level, every list either is a nil or a const. But we have variables in our universal data type. Now we compute with variables, so this is not an exhaustive case distinction, even if we from typing know that it has to represent a list. But that's not a problem. We can just add a default clause saying if none of these rules match, well, then it most probably will be a variable or anything where we can't apply any of the rules. So we can happily say, oh, then we leave the expression as it is, treat our function name as if it were a constructor, because in this case, when we know no rule is applicable, we know it will never cause a radix later. So we can just leave it as a symbolic expression, treating this function as if it were a constant, which is nice. And as I said, we want to also compile down term rewriting rules which we proved earlier. Say we might have proved that the append of list is associative. Then we have something like such an equation, which we also want to compile down. And now it comes handy that we just, in the case where we couldn't simplify, say, one of the arguments, say the sub-expression, then we just reproduced by taking the function name as an additional constructor, so we can match against that. So we match against these additional constructors and just use a normal ML pattern matching to add a rule like this. And note that even though in this case we know it will never cause a radical, here we of course use our function itself, not the symbolic representation, because in general the expression on the right-hand side might further simplify. That's the whole point of adding rewrite rules, that we can then, after using associativity, simplify even further.
How does the user, do you just go look for such rewrite rules, or does the user have to indicate which ones to use?
The user has to indicate which ones to use, especially as he has to prove them beforehand. So the way it is done in Isabelle is you prove a theorem, say you prove a theorem saying, saying this equation, saying append is an associative function. And then in the statement of the theorem, you add a qualifier saying code. So use this when generating code, wherever it's possible, which is only in this evaluation, not in the program generation. If you want to get approval with correct program from the Isabelle theorem, then it won't be used. But generally, you can say arbitrary theorems you proved, you can mark as use this information for code generation. And it will use it if possible, that is, if it's an equation, starting with some function. Yes?
2 slides ago, I think you motivated multi-arity functions, and I was
Yeah.
sort of wondering if you're going to have a multi-arity version of the program.
Sorry.
So there's one small overhead to this function is that the pattern match compiler will disassemble the list. We'll do
Yes.
it once for everything.
And can't do it just accepting that. So we're not making use of the fact that it's arity precisely twice, so we will always match against this pattern. The reason why we have multi-arity function is just that, there could be also some pattern here, and then you would have a more complicated pattern in this matching, but we'll always match against a single argument within a list. So we have an overhead per function call matching against the 2-element list, getting the 2 parts of the list out.
Right, but it seems like something that compiler could also do. You could have append list, and then could have, or append star, append 1, append 2.
Yeah. So, yeah, as I said, you could, instead of having this list approach, which is universal, flow 1, flow 2, and so on, compile it down, which isn't too bad, because first of all, you don't have that high arity anyway, so it probably won't be a very long list. And the other thing is, you do it, define the data type, or you only have to define this data type at the time where you're, at the time where you have the terms already you want to compile, so you can generate as many constructors as you need. And, slightly off topic, even if you want to say all these other functions I want to have ahead of time, and the nice thing is that ML contains one data type where I can add constructors at runtime, which is exception. So you could, instead of the universal type, use an exception, then add more, the exception data type. So that's what our first approach, saying, we have a type and we want to add more constructors at runtime. Then you could even, instead of having here a constructor matching against a number or a string, just add new constructors at runtime. Which is a bit a dirty hack, but it actually also works quite nice.
So there are all these papers on general ADTs. This would be one example of something that
So not claiming that it's
writing it GADT, but I see that your embedding is basically throwing away the Isabelle types.
Yes. So we do throw away the types, and we're not making any use of them. which on the one hand is, well, on the one hand is simple because then we don't have to deal with the types later, and it's and we're kind of independent of whatever type changes Isabelle might do in the future, which makes a very simple and short program and very easy and flexible to use. On the other hand, well, we're not making use of them. That is, we're not using the fact that we get two arguments. We're not using the fact that ahead of time we know it will ever always be a variable or always a constructor or always a closure, at least in some cases. So we have the additional overhead of, it's getting to the slides where I want, of matching against the two elements of a list. And actually also in the, if you remember the apply function, they also had a matching against whether it's a variable or whether it's a closure. And if you made more careful use of the type information, at least in some cases, you could anticipate the decision and pre-compile it instead of doing matching at every call of the function. So yeah, there is some overhead involved in it. On the other hand, it's nice and flexible, and that's why we choose that approach. Okay, and as I said, it works well. It's nice in practice, but as I said, we use it in a theorem prover. And actually, we use it as a part of the trusted computing base. So not only we use it to prove theorems, but also the way it works is that at some point you can say, oh, use this normalization tactic, or use this normalization. And then you compile, you look at the result, get your term back, do all the type inference to make sure you have a correct typed Isabelle term. And then you just say the theorem prover, oh, we've computed this normal form, so believe me, this equation is true. So we're not generating any proof from our normalization. We just do it and say, believe us. So we better try to prove that it's correct what we've done, or at least convince ourselves that we haven't done it incorrectly, for otherwise we would introduce inconsistencies in the theorem prover, which normally isn't a good idea. So as I said, we modeled our implementation and proved at least a minimal correctness requirement. That is, if you ever happen to get an answer, then the equation you get at least is a consequence of your theory, which is enough to keep your theorem prover sound. It's not all you want. Normally you would say, I do get an answer, and actually I get the normal form as an answer, not just any term which is equal with respect to the theory. But at least as long as you're only interested in sound of the theorem prover, that's all you need. And I'd also like to show the proof because it's quite a nice idea. So, well, as I said, we model what we did. So we model a part of ML, pure functional part, so we're not dealing with any assignments or similar. And then we just take our representation of the internal state of this ML evaluation mechanism. And for every such internal ML state, we assign a term. And then this ML state changes over time because of the ML evaluation reductions. And we keep as an invariant that, or we make sure that this denoted term only changes according to the equations of the theory. So the invariant that we have is that the internal ML state represents a term that is modulo the theory we started with equal to the initial term. Okay, let's go a bit about the modeling. So first of all, which part of ML do we need and how do we model it? Well, there's ML has internally some form of lambda calculus. So we have ML variables, ML function application, function abstractions, and ML applications of function. Then as we compiled a couple of functions into the ML level, like the append, the minimum, and so on, the function of our object theory. And it might look scary the way it is, but we actually do take care of names and never clash with any predefined ML function or function of the Isabelle implementation. And then we had this data type, which I was talking about, where we had our constants, variables, and closures. And then we had some special functions that played a special role in our implementation, which are precisely two. This is the apply function, which, well, essentially checks whether it's a closure or a variable, and then correspondingly models the application in our universal data type to make it a model of the lambda calculus, and this function term, which takes an element from this universal data type and gives us back a syntactical representation of this a priori semantical object. And as I said, for each such internal ML object, we mathematically assign a term that it represents, and then make sure this term only changes according to the rules. So what are the corresponding terms? Well, variables, ML variables should in some way correspond to term variables, ML application to lambda application, and, well, abstraction to abstraction. The compiled functions stand for their syntactical counterparts. And there's the universal data type, and I already mentioned what it is. If it's a constant, well, then it's with some values, it stands for this constant applied to these values. If it's a variable applied to some value, it stands for the variable. And if it's a closure, it stands for the function denoted by that function with maybe some arguments accumulated. And our apply function is meant to model the lambda calculus, so it stands for actually applying the denoted terms. And the term, well, it gets a term representation, but of course it denotes the object itself. And now we look at, well, in the proof we look at all the transition that the ML machine can do. And here I do two typical examples and see that the denoted term only changes according to the rules. Well, one interesting case is the apply function, where say one of the clauses was if we apply a closure to some value, well, then we use ML applications with that interpretation what everything is supposed to stand for. Well, that definitely is a true equation. The first thing stands for f applied to v, and the second thing as well. So that was easy. Well, with the compiled function, we compile the rules 1-1 in the same way. And the other interesting thing is how do we, which is, I think, the most fascinating thing about normalization by evaluation. How do you get a term representation of a semantic function? So the term representation, if it's a function, as we said, we take a fresh variable, whatever fresh means, and then we get a lambda term, this variable x. So we take a fresh variable, apply it to this function, get a term representation out of it, and then bind it at a syntactical level. And what does it stand for? Term stands for the denoted, the closure stands for f, so it says f. And on the right-hand side, we have lambda x, f of x. So that's just eta expansion, which is also true in our theory. And I said for the compiled rules, it's just the rule itself. So and that's my last slide, but I'm open for questions. So as I said, we implemented it, and it's quite short piece of code. The kind of the interesting lines I've shown on the slide. And the rest is, well, partly this code generation, walk over a term and represent it as an ML term. And about half of the code is something like bookkeeping of variable names and things like that. Well, half of the term that isn't comments anyway. And it works reasonably fast. So Isabelle already had some symbolic evaluation at doing just term rewriting. So taking the term, looking whether the term rewrite rule matches, transforming the term, and repeat until you can't apply a rule any further. So we're about 100 times faster than that. But as I said, there's also this completely compiling down to ML and running at ML level, which works as soon as you don't have free variables. And if you have an object of ground type, then we're slightly slower. As discussed, there's some overhead with the matching against lists. I think we recently got a reasonable use of it in the case where you have to deal with free variables but still want to be efficient. The other thing discussed is, well, we used an untyped setting for normalization by evaluation. So we throw away all the Isabelle types, which is nice in the sense we're flexible. We don't have to think about too hard what the Isabelle types mean. We just throw them away, do untyped rewriting, and now we can reconstruct them. Or we just see if we can reconstruct them in a unique way, then that's the correct term. Otherwise, we say, oh, better be careful. We don't claim anything about it. But as there are some additional administrative reductions like this apply closure f, which you do some pattern matching before then do the actual function call. And in some cases, you can avoid that if you use type information. I think in the most traditional way, it's just normalization evaluation for simple types. They can get completely rid of these additional matchings. And there's a bit of work going on, well, aiming at conditional rewriting, but what turned out to be very useful is to add some support for non-left linear rules. So the typical example, if you have an if statement that both branches happen to be the same, then you want to simplify it to, say, the then branch. And the way...
Parse
Well, what's the parse of this?
Okay, that's all I said. So what we actually do, that's why I've written it in this Haskell-like notation. If you have a symbolic expression, so this part is meant to be a symbolic. So you have a term of that type, and you can prove that A equals B, so both branches are there. Then you can simplify it to A. And that's also how we do it. If we have a non-left linear rule, then we make it left linear by just renaming things differently. And we have a decidable under-approximation of equality. That is, we have a predicate that if it returns true, then we know for sure that the terms are equal. But on the other hand, it doesn't spend too much effort, so it's still fast. Essentially, it says, oh, outermost constructors I know. If they're equal, then I can look at the arguments what they're applied to. And if it's a function, I don't bother to look into them. I just leave it as is and say, I can't prove they're equal. Which is an under-approximation, well, which has to be because semantical equality is undecidable anyway. It works reasonably fast and covers the cases which are most common, especially if just both branches are free variables and happen to be the same variable. And these are the useful cases, and you want to apply them. Yeah?
So, can I ask more questions?
Yeah, sure.
So, the notion of equality after the embedding what's ML equal is not extensional equal in Isabelle. So do you have a notion of you can define functions using extensional equality?
At which level, or what do you mean by?
So there's a notion of equality built into ML.
Yes.
And there's a notion of equality in Isabelle.
Yeah.
If you map it naively to ML equality,
ML equality,
everything should break.
Yes. Should break in the sense that there are ML objects which are not equal as ML objects, but
Will be
extensionally equal at Isabelle level.
like
Yes.
this associative append with variables.
And things like that, yeah.
And
So what we do is we under-approximate. We use something slightly, we don't use the ML level of equality. So we actually do compare constructors and so on. So we're not just saying, oh, equal pointer. But it's an under-approximation. We only do those things which are fast to compute. That is, if it's the same constructor, same variable, but we don't look into closures, where there's no sensible notion of equality anyway at ML level. And for that, we know if it's equal in that sense. It definitely is equal in the Isabelle sense.
can you say a different question? So Isabelle has, you can define, can you define rewrite rules with nonlinear occurrences of variables, say the same variable?
Several times, yes.
And you compile that into ML pattern matching?
No, we compile it actually in a way pretty much as it's there. So let's do an example on the whiteboard. I guess the rule which motivated adding nonlinear equations is Isabelle's definition of equality. You have an equality sign, and you probably can prove a rule like this. Oh, let's get it right with the various forms of equals true. Equality XX equals true. So that's, if you want to have such a thing in your language, say at a test you want to predicate something equals itself simplified to true, then that's a nonlinear rewrite rule. And the way it's equality is probably, well, that's the thing motivated, but just assume that this is some function where you have a rule like that. And the way we compile it into ML is saying f of xy equals, and then, so these are variables at ML level. This is the function corresponding to that function symbol. And then we actually take our approximation of equality. If, as I said, this under approximation, which if it returns true, then the things denote equal terms, and otherwise you can't be sure. If these happen to be equal, then we take x, else, well, continue pattern matching. So we'll call the next function f prime, where f prime is, well, that's the next pattern matching. Usually it will be the default clause, something like that.
True or whatever the function is.
Return, yeah, true. Then true, else, continue with the pattern matching. So you have no guarantee that if you go to the next case, these things are actually different, but you will still be sound in the sense you only apply that rule if you can prove these things denote equal objects.
Is it common to have associative commutative properties in
So we don't do AC.
Compiler does nothing to AC signals.
No, it doesn't. But actually, with associativity isn't that bad, because before we enter into this position where we say, oh, we test for equality, these things are already objects of a universal data type, though they're already canonical with respect to associativity. If you remember the definition of our how we compile the apply function. Can I go back?
Maybe you can apply some AC rules.
So as I said, before we do this test, all these x and y will already be evaluated to an object of our universal data type. And if they happen to be something where associativity is applicable, then probably this rule will have fired first and things will have already be simplified. So if you prove associativity, then both x and y will be canonical with respect to associativity. And that's very easy. Commutativity is more difficult because you can't just add a rewrite rule. Oh, if nothing else applies, then try to do it the other way around, because that won't terminate.
But then it seems that you don't necessarily get something that's really unique normalized. I mean, if I take something I wrote in mode, which is AC rewrite,
Yes.
I would expect more to apply AC rules exhaustively and cleverly. And do you have such a theorem that you would be able to apply?
So far,
Commutativity. Okay, so we add commutativity, and then you have
a problem.
complete arbitrary permutations of arguments.
So no, we haven't done anything in that direction. And as I said, associativity isn't that bad because you can just add it as a rewrite rule and it will still keep terminating. With commutativity, you can't do that naively. Just adding here commutativity, it won't terminate. And in general, that's a problem if you allow the user to add arbitrary, well, at least proven rules as rewrite rules, arbitrary proven equations as rewrite rules, then it still will be sound, but if you do it in a stupid way, you immediately lose termination if you add arbitrary equations as rewrite rules. So there we have to rely on sensible use of that anyway. The only thing we currently guarantee is that it's sound. So if you get a result, then at least it's correct. And the other thing which you can prove, even though we haven't finished fully formalizing, is that whenever you get a result, it will be normal in the sense that it doesn't contain any beta radix, well, obviously, and also that none of the rules is applicable. So at least whenever you get an output, it cannot be simplified by any of the rules given.
Suppose you want to just recap normal form.
Just recap normal form. So currently we don't have it, but I guess it's
the unifier, the unification algorithm.
Yeah. So of course you can have various tactics and so on, but not at. But as far as I know, they're all only at the symbolic level. So working with Isabelle terms. Even so, in the MBE approach, it wouldn't be that hard. The only thing you would have to change is this term function. Because the compilation, I think I was skipping to it. The compilation itself doesn't trigger anything. Is it? I should be careful. So you would have changed things if you're only interested in weak hat normal form, but it wouldn't be that hard. So essentially, it means that if I have a closure here currently, this application is what is enforcing that the thing is normalized any further. So you could change the type to not only contain the closure, but also a symbolic representation of it. And yeah, so well, at least in a lazy language you could delay. Well, symbolic representation isn't that hard to get if you start from a term in the first place. So this function is obtained by compiling a symbolic term into ML. Well, if you have the symbolic term, it's easy to get a symbolic representation. Just keep the term. And then at this place, you can say instead of, I take a new variable and then apply it and normalize what is under the lambda, because that will always get your lambda. And if you want weak hat normal form, at that point, you would store symbolic representation here. And at this point, just return the symbolic representation and throw away the closure. But yeah, that's changing. So in the end, we're not doing anything but building a new compiler for the language itself, and then we can change how far we want to compile, what we want to include and what not.
For your rewrite rules, if the user proves that some equality holds, maybe that equality doesn't always hold. Maybe it holds only under certain circumstances. One could imagine that what you would compile it into would be not just something that matches where the ML code would match, but it would also check some other condition. Do you do that anyway?
Well, let me give two answers. First thing I said, we aim at some form of conditional rewriting, which we kind of add anyway if we want to do non-left linear rules. And
but there is a very special case, maybe, right?
Yes. But the general mechanism of saying, I have an equation, then make a test and otherwise continue pattern matching. Instead of using here equality, you could add other tests. So that's why we came up saying, well, if we're that far, then conditional rewriting isn't. It's just a small step. But what actually is now happening, or is already present, is that this code generation keeps very much track of the context. So if you've proven a rule under some assumptions, so say you're in the state of a proof, and in that state you have an equation, you want to use it as a code lemma, then it's only included in the code generation for that part of the proof state. So you only include the lemmas where they are valid. So if they depend on some assumption and you want to include them, then as soon as you close the context and you don't have this assumption anymore, and you then evaluate the term, you will generate new code, which then doesn't include that. So Isabelle currently takes a lot of care of tracing the context and generating the code appropriate to that context. So in that sense, you have it. And also, at the global level, you can later decide, now I don't want to have that in the code lemma anymore because it slows down or it doesn't give me the form I want. So you have a state of what are the equations currently relevant for code generation, and then it's generated over and over again once you use a function with different state or different context.